Okay, welcome to AP Calculus. This is 6.2. It says 6.2a, but don't expect a 6.2b. This is the only section from 6.2, the only lesson. One thing we only have 4 sections in Chapter 6, and Chapter 6 is an awesome place for you to put a really strong grade on the board when we test this. It's foundational though, so understanding this, moving into Chapter 7 is going to get a fair amount more difficult than 6, but we really need to understand concepts, and we're going to be working with these areas. So one of the things we've been doing is we've been taking curves and subdividing that by, like, in this case, LRAM. We've been subdividing that by LRAM and approximating areas under curves. And in this case, maybe my partition widths are by 1/2, so all of these are 1/2. And our sum would be 1/2 times the height 1 times the height 2 times the height 3, height 4, height 5, etc. So we've been doing those types of problems, and we haven't been talking about this summation symbol, but you guys have seen this before. You guys at this stage have seen something like this. Let's say we got the sum as k equals 1 to 4 of 3k. Be 3 times 1. We put in 1, it's like a staircase. We go from 1 up to 4. We take 3 times 1 plus 3 times 2 plus 3 times put in 3 plus 3 times put in 4, stop. And what we might do there, if we notice this 3, I can factor it out, and I just get 3 times 1 plus 2 plus 3 plus 4. Ends up being 30, but my point is, that is what we've been doing here. So this would be like the width of our partition, and this is each of our different heights along the way. So we've been dealing with this. We just have a nice way of indicating it now. So ultimately, what are we trying to do with our partitions if we want to get better and better and better accuracy on our approximation of the area? We need more and more of these. So rather than write out 1,000 of these or 1,000,000 of these, or heaven forbid, infinity of these, we got a little symbol here we can use. So what's our goal in calculus in approximating? We'd really like k to be 1 to infinity. The problem with that is that these get so narrow they become virtually 0, so we get no area at all. So that's the whole study of calculus. All right, so some rules about these. If we have a constant, we can just pull it out. Well, that's exactly illustrated right here. I could write this constant 3 in each term, but I also could factor it out. So we can pull the constant out and then just deal with this times, put all that in parentheses. No big deal. Constant value rule, this is kind of that in reverse. If I have a sum, a to k equals n times c, if a to the k has a constant value, c. No big deal, it's really kind of that in reverse. The sum rule is exactly what we would hope it would be. The sum of a function plus a function is just the sum of the first function plus sum of the second function. That also works for subtraction. And the difference rule, there it is. Okay, no big deal. We just got a lot of notational things to look at here. Now, these are formulas you may use. We actually last year in pre-calculus and honors pre-calculus probably proved each of these using induction, which was probably very, very interesting to you, or not, I guess. But there's some rigor to them. It was very new to you, I should say, last year. And these are just rules in case we get a special rule. For instance, let's say I want to add the numbers 1 through 88. This will be represented as k equals 1 to 88 of k. So that would be 1 plus 2 plus 3 plus 4 plus ... plus 88. Or it would just be 88 times 88 plus 1 on 2. Likewise for the sum of the first n squares. 1 plus 4 plus 9 plus 16 plus 25, etc. If that's the first 5 squares, I can just go 5, 5, 5, figure it out here, and the sum of the first n cubes. You may need access to those for the homework set. All right, the definite integral and Riemann, pronounced Riemann sums. Well, we're trying to find area under curve from A to B. We've been dealing with this. We just haven't seen this notation. Now, P is our partition size. This little looks like magnitude P is our partition size. Our goal is to have those partitions get smaller and smaller until they approach 0, and then we get a more accurate area along the way. But it can't really be 0. In fact, our goal of this would be 1 to infinity, however many partitions it takes us to get through. And then we have all of this notation. That's delta. This is just dx, and this is just f of x right here. You can read through this and try to make some sense out of it, but it's going away. Existence of definite integrals. All continuous functions are integrable. Now, it doesn't say continuous and differentiable. So if I have a continuous function with corner points or cusp points, it is integrable. Kind of makes sense, because what is an integral doing for us is just finding area under curves. It doesn't mind finding this area underneath there. Okay. So the definite integral of a continuous function could be written like this, and will be for this section, and you may not see that again. Ultimately, we're going to take this and we're going to turn it into this. Right here, this would basically be the integral from 1 to n of f of x dx. This is equivalent to that. So this guy just says we're finding the area under the curve f of x from a to b. Now, this is a really important thing in understanding. We all know that f of x is just a fancy name for y, and dx is change of x. So change of x is a horizontal component, so that's like an x. And our rectangles that we have been building have their height y, and this is our change of x. That's our increment. So this is just finding the area of all the rectangles we can fit in from A to B, and in the theory this is actually infinity rectangles once we move into calculus. And there's a lot of discussion that gets us from here to here, but this is what we need to understand. This is y times x. This is a y value times an x value. That's one of our rectangles. Okay. Area equals the opposite of a to b when f of x is below 0. So the integral of f of x, let's say my curve, this is y equals f of x. Here's my curve right here. So I've got a curve, and let's say we're just looking from here to here. So we're looking for this area. The integral of that will be negative, but the area would be the opposite of that, because the area is positive. Area is always positive, but the integral value would be negative when the function is below 0. Okay, integral from a to b is the area above the x-axis minus the area below the x-axis. So if I have a function that does something like this, from here to there, I've produced these areas. Call this area 1, call this area 2. Those are both positive values, they're areas. Well, the integral from here to here would be a1 minus the area below the x-axis, a2. And it'll be calculated in. We won't even have to do anything special with that. Unless we need to find the area, then we'd have to find this area, add the absolute values of those together. But this will calculate out in the integral as a negative portion, positive portion, so these will be battling each other. Sometimes that's a good thing. Let's say it's profit loss. So profit would be represented above, loss there, so revenue would be generated. You know, if my loss is a negative, so we just add those guys together. So sometimes we like it being as the negative. But if they're asking about areas, it's absolute value of this plus absolute value of that. We'll talk more about that. The integral of a constant, if f of x is c, so let's say f of x is, to make it more simple, let's say we've got a to b and this is 7 dx. And we're going from a to b. So let's draw that. The graph of 7 looks like this. So let's say a happens to fall here and b happens to fall there. What is our area? Our area would be the height is 7. The distance from here to here, I don't know, it's a to b. Well, what if this was 3 and this was 8? I'll bet immediately you would know that that is 8, that is 5. Oh, it's b minus a. So if it's not 7, if it's c instead, it's just going to be c times b minus a. All right, that makes sense. Don't have to memorize that. That's nice. Okay, so first thing we're going to do, we're going to turn this guy into our more friendly integral symbol. So the integral symbol basically takes care of all of this. We have the integral. CK, you can think of that as x. That's x squared dx, and we want where p is a partition from 0 to 2. It's that part of the curve. We're going 0 to 2. That's it. So we're just changing this into the form. There's a lot of explanation behind why this finds all the areas for us. But basically that's finding infinity rectangles on a partition. Okay, of the whole curve. Okay, so give this one a try. If you have followed that, this should take you about 5 seconds. There's our integral, our function, ck, 1 on x, dx, from -7 to 5. And we'll be talking about what we do with that. Okay. Evaluate the integral. Now, they want us to do this with graphs. There's going to be an easier way. Well, there's going to be a more mechanical way, but right now we're going to talk about the really beautiful marriage between calculus and geometry. So I want the function 5. Well, the function 5 looks like this. But I'm interested in the area between -2 and 1. So I'm looking for this area. Well, that area, pretty simple. This is a height of 5. This is a length of 3. So the area is 3 times 5, or 15. I don't see any real reason to just go through this whole memorization of our constant rule here. Oh yeah, it's C times B minus A. I've got to remember all that to do this. No, it just takes a second to, eventually we'll be able to just kind of have a vision of this. Oh, it's a height of 5, and we go from -2 to 1. We're on a run of 3. Oh, it's a 3 by 5 rectangle. Likewise, we're evaluating the integral. At -160, we're down here. We're interested in 0 to 3. We're interested in this area. And that area is 160 times 3, 480, but the integral, because it's below the x-axis, is negative. Okay? All right. 3a. This function, this is y equals square root of 1 minus x squared. I want to draw it. And maybe I don't recognize what y equals 1 minus x squared is. So I'm going to try to manipulate this algebraically. How about if I square both sides? And now I'm going to add x squared to the other side. I'm like, oh, I know what this graph wants to be. Now, stick with me here. This graph wants to be a circle centered at 0, 0 with radius 1. It wants to look like that. But if I was to go backwards from here to here, I'm going to get y squared equals 1 minus x squared. I'm going to take the square root, but in solving, when I take the square root, I have to go plus or minus square root of 1 minus x squared. And this is only the positive version. This is the full circle, plus being the top half, minus being the bottom half. This is just the top half of that circle. And we should have had a problem anyway, because I was talking about y being my function. We can't have a circle and have it be a function. Does not pass the vertical line test. So we are just talking about this area. And it's above the x-axis, therefore it's positive, and it's half a circle with radius 1. The area of a circle is pi r squared. So our area is pi times 1 squared, but it's only half of the circle, or pi on 2. That is the value of the integral. We don't say the value of the integral is pi on 2 square units. If it asks for the area of the circle is this. But oftentimes, an integral gives us total distance. If it's a velocity graph versus time, the integral gives us distance, not area. So, granted, it's found from the area. So that's kind of a mindset. All right, let's see if we can get a graph of this guy right here. I know I'm only interested in -1 to 1. So I'm going to put in some values. If I put in -1, absolute value becomes 1, 1 minus 1, 0. If I put in 0, I get 1 minus 0, 1. If I put in 1, I get 1 minus 1, 0. I think I know what this looks like. If I put in a half, I get 1 minus a half, a half. If I put in -1/2, it's the same as putting in +1/2. So I am convinced this looks like this, and the area we're looking for is a triangle. We're looking for the area of a triangle. Area equals 1/2 base times height, or area equals 1/2. Our base is 2, our height is just 1, so it is 1. That is the area. But the integral, we'd say the area is 1 square unit, but the integral is just 1. It's 1. I don't know what it is. It could be 1 foot, could be 1 mile, could be $1. Lots of different things it could be based on the problem we're trying to solve. Okay, use FN int to evaluate the expression. So that is located on your calculator. If you have an 84, it's a little bit slicker. I'm going to show you what you would do if you do not have an 84 here. But if you have an 84, a little slicker than an 83. So I'm going to go to math, and you would do this on an 83 as well. There is FN int. You might have N int, but I think it's FN int on an 83 as well. As soon as I do this, presto, I want to put in 0 here. I just toggle around. Up here, put in 5. For my function, I want x divided by parentheses x squared plus 4, close parentheses, and we're dealing with dx. Now, if you have an 83, how you will enter that is you would do FN int, same thing, through your math. Then you would enter the function x divided by x squared plus 4, then you would comma, then you would enter 0, then you would enter 5, then you would enter x. Now, I need to double check this. If that does not work for you, maybe the x goes before the 0. But I think this is it. Okay. So if you don't get this value that I'm about to get, put the x in front of the 0, x from 0 to 5. All right, back to here where we can see it nice and clearly. I enter that, and I get AP Calc test. If we're rounding to 3 decimals, 0.991. So is approximately 0.991. Okay, we'll brighten this back up a little bit here. Got it? And find the area enclosed between the axis, x-axis, and the graph of 4 minus x squared from x equals -2 to 2. Find the area of this. So example 4, this is part B, we're still using FN int. So this would be, I'm going to set up the integral first. We want the integral from -2 to 2 of 4 minus x squared. Do the parentheses need to be there? Yeah, they need to be there, because how are we thinking about this again? That is the height, that's our y value. This is our x value of our rectangles, and we're adding infinity of them together when we're doing this. Okay, so back to this. Darken that up a little bit. So I'm going to go back to, where was it again? It is in math. It's math 9. Might get used to that soon. I'm going from -2 to 2. I'm going 4 minus x squared dx. Enter. And I get 10.6 repeating. So this is approximately 10.667. That's our approximation. And that's also a big moment. So this is a preview of what we're going to be doing. I'm going to go back to here. This is not in this section, but it's in the next section, and it's in the rest of the semester. We're going to find this integral, antiderivative. If I ended up with a 4, I started with a 4, or with a 4x. The derivative of 4x gets me to 4. If I ended up with an x squared, I must have started with an x cubed, but the derivative of that would give me 3x squared. I don't want 3, so I put that on 3. And it wouldn't give me a minus, so I put a minus there. Then we take that negative 2 to 2 and we bar it over here. And how we treat that is we put 2 in for x into this thing. So I get 4 times 2 minus 2 cubed, 8 on 3, minus all of, put in negative 2, 4 times negative 2, minus negative 2 cubed, that's negative 8 on 3, or I get 8 minus 8 thirds minus negative 8 plus 8 thirds. Let's see here. That is 8 plus 8, 16. That is negative 8 thirds minus 8 thirds minus 16 thirds. So quick jump to our calculator here, and I get 16 minus 16 on 3. Come on. I didn't put 16 on 3. Boy, that was almost really disappointing for a second. 16 minus 16 on 3. Come on. 10.6666667. There we go. There's a look at your assignment. Let's make certain we are 100% on this. These are the fundamentals that the rest of the semester are built upon. We cannot afford to be pretty good at Chapter 6. If we're pretty good at Chapter 7, that's pretty good. If we're pretty good at Chapter 6, that's pretty bad. Okay, let me know if I can help.